This is another video in the series for Math 1073 for UTSA. Today we're going to be talking about Module 5.1, which covers more topics on power and polynomial functions. So the first question or problem says, for the following exercises, determine the end behavior of the functions. Okay, so looking at this first one, f of x equals x to the fourth power. Because of the even exponent, negative outputs and positive outputs give the same result. So my end behavior will be the same on the left as on the right. So basically, I look at the leading coefficient, which in this case, there's an implied 1 as the leading coefficient. And since the leading coefficient is positive, and I know that the two end behaviors are the same, this means, oh, the positive infinity is the end behavior on both sides. So the left end behavior, as you follow the graph out to the left, this will be infinity. The graph goes up. So depending on the context or the book you're using or whatever, you could say infinity because that's where the y-coordinate goes, or you could say up because that's where the y-coordinate goes up. And then the right end behavior is the same thing, either infinity or up. In short, the graph looks something like this, up on both sides. Now, in the middle, there might be a W shape or something. There might be some other stuff going on in the middle. The end behavior is about what happens at the ends. And so we don't really care about what's happening near the origin when we're talking about end behavior. So you can have two totally different functions, but their end behavior could be the same because they aren't the same near the origin, but out far to the left and far to the right, they are essentially the same shape at least. So this one, f of x equals x cubed, similar idea, but since I have an odd exponent, then when I plug in an odd number, or sorry, a negative number rather, the result will be negative. If I plug in an even number, positive number, positive number, it's true that if you cube an even number, it will be even as a result, but that's not relevant to end behavior. If you plug in a positive number, the result is positive. If you plug in a negative number, the result is negative. So this graph looks something like this. If you follow the graph out to the left, it goes down, and you follow the graph out to the right, it goes up. So the left end behavior, following the graph out to the left, well, this would be negative infinity, or in other words, down. And the right end behavior, well, this would be positive infinity, or in other words, up. Again, in context, probably in web work, infinity and negative infinity will be the expected inputs, but up and down are also descriptive, and sometimes it's useful to call it that. Okay, part C. So here we have a polynomial that is not in standard descending order. This has been factored, so we need to distribute in order to figure out what the end behavior is. So I'll distribute this negative x squared onto all three terms, which you might wonder, is that really necessary? And we'll address that in a moment. So negative 2x to the fifth plus 3x to the fourth minus 2x squared. So when we go to look for end behavior, only the leading term matters. These other terms don't affect the result. So really, did I need to find them at all? Well, if we only care about end behavior, then no. Since they do not contribute to end behavior, if that's all I care about, then I don't need to worry about them at all. So we'll ignore those terms. They aren't necessary. So I notice, oh, this is an odd exponent. So it's going to have sort of an S shape like the previous example did. But I have a negative leading coefficient. So if I plug a negative number in for x, raise that to the fifth power, you get a negative number. But then you multiply by negative 2, you get a positive number. So that means that the left end behavior is up, or positive infinity. If you plug in a positive number, raised to the fifth power is still positive, times negative 2 is negative. So then the graph will go out down to the right. Now in the middle, the other terms affect what happens in the middle, basically. But the leading term affects end behavior, and the non-leading terms primarily affect the behavior closer to the origin. I'll gloss over some details, but that's basically it. So our left end behavior will be infinity, or in other words, up. And then the right end behavior This will be negative infinity, in other words, down. There is other notation for this, which we'll address after the this example here. So for this one, we have an exponent of 7, but it's being applied to a binomial. So there's a couple ways to deal with this. One way is to notice the thing that had happened over here, that only this leading term within the parentheses made its way into the term that became the leading term. Okay, so if you have a couple of polynomials or power functions multiplied together, then from each factor, it's only the leading term that will appear in the resulting leading term. So here, this minus x is the leading term among the inside of the parentheses. If we ignore the 7 temporarily, if we just had 2 minus x, well, minus x would be the leading term. So when you have an exponent or any product like this, then really the leading term inside each factor is all you care about. So if I really wanted to, and I guess I will in this case, it'll be tedious, but that's fine. I could write this out as 2 minus x, 2 minus x. I'm starting to regret this already. 2 minus x, 2 minus x, 2 minus x. Almost done. 2 more. 2 minus x, 2 minus x. Okay. In each of these, only the minus x has the possibility of making it into the resulting leading term. So if I just throw out the 2's and ignore them, I will still get the correct leading term. So this equals negative x to the 7th plus some other stuff. What is it? I don't know. And I frankly don't really care, because we're just being asked about end behavior. And only the leading term determines the end behavior. So I don't really need it. So now I can focus on the leading term and say, okay, I have an odd exponent. So I'm have sort of an S shape rather than having like a U shape or an N shape, right? Even exponents will always give you, let's do this, change colors. Even exponents will always give you like this, right? And then odd exponents will always give you like this, sort of an S shape, or a sort of a 5 shape, the way I've drawn it poorly. That's a little bit better. Okay, there we go. Somewhat better. Okay. So since I have an odd exponent, I know I must be getting one of those two options. The two end behaviors are different, in other words. Okay, so now the negative in front tells me, oh, I'm getting this one. Okay, the negative coefficient. So my left end behavior, in fact, maybe we could even summarize this. My left end behavior will be infinity or up. My right end behavior, this will be at negative infinity or down. Okay. Do we have room to summarize this? Yeah, sure, we can summarize it here. So the idea I was getting to here, we'll summarize slightly differently. Okay. So I'm going to make basically a grid. Let's do it this way. There we go. Sometimes the interface is squirrely, and so I spoke too soon, apparently. Okay. Okay. So if we have our say even degree versus odd degree. Okay, and then we have positive leading coefficient versus negative leading coefficient. Okay, if you have even degree and a positive leading coefficient, then you get this shape. Okay, If you have even degree and a negative leading coefficient, then you get this shape. If you have an odd degree and a positive leading coefficient, you get this shape. And again, um, the behavior near the origin could have a bunch of bumps in it, but we're not worried about that right now. We're just worried about end behavior. And then if you have an odd degree and negative leading coefficient, you get this shape. A little wobbly, but it's fine. And again, the part near the origin could have lumps in it, but I'm not worried about that. So there you go. There's a summary of how the degree and the coefficient interact to create the end behavior. Okay. So number 2, for the following exercises, determine the intercepts of the functions. Okay. So this one, if I want the intercepts, I want all of them, I could find the y-intercept first. And for the y-intercept, well, if you think about it, let's do this off to the side real quick. Let's go over here. If I have a y-axis and an x-axis, right? The x-axis measures the distance. It doesn't want to work with me. The x-axis is like a ruler that measures the distance from the y-axis and vice versa. The y-axis is like a ruler that measures the distance from the x-axis. So if we have some graph, some function like this, right? Then this ordered pair here, where the graph hits the y-axis, well, the x-coordinate would have to be 0. Okay? And here, this point where the graph hits the x-axis, well, in the ordered pair there, the y-coordinate would have to be 0 because the y-axis ruler measures the distance from the x-axis. Well, if you're on the x-axis, then the distance would be 0. The vertical distance would be 0. If you're on the y-axis, then your distance from it is 0, so the x-coordinate is 0. Okay, so if we want to find a y-intercept, just plug in 0 for x. So y equals 4 times 0 plus 1 times 0 minus 2 times 0 plus 3. So I get 4 times 1 is 4 times negative 6. I get negative 24 for my y-intercept just by plugging in 0 for x. Now, if we plug in 0 for y instead of x, and of course, y and f of x are sort of interchangeable. Y is the variable of the output. F of x is it's basically giving the formula f of x equals what the formula is, but then also just the expression f of x emphasizes the name of the function and the input variable, but f of x is always equal to the y coordinate. Okay, so then we'd say, okay, well, we want the x-intercepts. We'd say 0 equals 4 times x plus 1 times x minus 2 times x plus 3. Okay. So which x values do that? Well, one way to say is to look and go, well, if this factor is 0, then the whole right-hand side is 0. What number would do that? Well, negative 1. If this factor was 0, then the whole right-hand side would be 0. What input number would do that? Well, 2. And then the same here, the input would be negative 3. Another way to write the same idea is to say, let's break up that equation into 3 equations. And any one of these could be the solution that we want. And I'm writing or because in the sense of like an application problem where you're going to get a single answer, you don't know which one you want at the beginning. You just, well, I'm going to want one of these. I don't know which one necessarily. So I have to say or, because it could be any one of these equations that results in the number that I ultimately end up using as, oh, here's my result. I found the solution to this application problem. Conceptually, though, of course, x can't be both negative 1 and negative 3 at the same time, but at one time it could be negative 1, and another time it could be negative 3, and another time it could be positive 2. So I'm saying, well, any one of these factors could be 0 at a given time, just not all at the same time, because x cannot be both negative 1 and negative 3. Anyway, so I can solve each of these equations individually now. So negative 1 equals x, 2 equals x, and negative 3 equals x. So I found my y-intercept and my 3 X intercepts. Okay, what's the next one? F of x equals x times x squared minus 2x minus 8. Okay, so if we want the y-intercept, I'll plug in 0 for x. Of course, 0 times anything is 0, so y-intercept is 0. Whenever your y-intercept is 0, that means also one of your x-intercepts will be 0, which we'll see in a moment. So to find the x-intercepts, I'll set the function equal to 0. And there's two ways to go from here. You can either start by factoring as much as possible, which I think we're gonna do in this case. Another way is if it's not obvious how to proceed by factoring, and your equation is partially factored already, you can go ahead and separate the factors, much like we did over here. I separated the factors into more than one equation. You can do that sooner rather than later. The order in which you do things is up to you. I'm going to go ahead and factor this one completely, though. So let's say 0 equals x times, well, x minus 4 times x plus 2. Okay, so now I can separate these factors into separate equations. Clean up some of this writing a little bit. There we go. Okay. So this one's done being solved. There's nothing to move, and I can solve these two separately. So 4 equals x, or negative 2 equals x. So we get 0 for our y-intercept. 0 is also an x-intercept. And it might seem redundant to list it twice. Oh, so why is 0 listed twice? Well, it's both an x-intercept and a y-intercept, which conceptually are different things, so we should list it twice. And in particular, on the online homework assignment, you probably should list it. Like there are two parts to the question, and it wants all the intercepts in part. It wants y-intercepts in part A and B, x-intercepts in part B. List 0 in both because it is in both categories. So there are intercepts. Okay, so for the following exercises, determine the number of turning points and least possible degree of the polynomial function shown. Okay, good. So basically, the number of turning points, let's rephrase that. There's two ways to say it. Basically, the degree is at least one more than the number of turning points in a graph. It could be higher, potentially. Like if you look at the graph of y equals x to the fourth, it has one turning point. Okay. If you look at the graph of y equals x squared, it has one turning point. If you look at the graph of y equals x to the sixth, it has one turning point. So really, if I make these all negative, any one of these could be related to this graph. The leading term could be negative x to the fourth, negative x squared, negative x to the sixth. Okay, that's a possibility. We don't know which one, but I can look at this and go, there's one turning point. The degree is at least 2. So turning points, oops, 1, degree, put it this way, degree is greater than or equal to 2. It's at least 2. Is that the way the question is asked? Least possible degree. Let's do this. I would express it this way, degree greater than or equal to 2, but least possible degree 2. It's possible that in the online homework, you're not going to give an inequality. You're going to give just the least possible degree, with the understanding that, well, it could be more than that. That's what least possible means, of course. Okay, looking at this one, we've got 1, 2, 3 turning points. Okay, so turning points, 3, least possible degree, one more than that, 4. Now this could have a degree that's greater than 4. It couldn't be 5 though. Notice that the end behavior is the same on either side. So the degree cannot be odd, it must be even. So the degree could be 4 or 6 or 8 or 10. But it could not be less than 4 and it couldn't be odd. Okay, for this one, yeah, 1, 2, 3, 4. Okay. So the degree is, sorry, the turning point's number is 4. And then, so the degree, least possible degree, is 5. And notice that the end behaviors are different. So for this one, the degree must be odd. It can't be even. But the degree could be 7 or 9 or more, just not even. Okay, so this one. An oil slick is expanding as a circle. The radius of the circle is increasing at the rate of 20 meters per day. Express the area of the circle as a function of d, the number of days elapsed. Okay, so the radius of the circle is increasing at a rate of 20 meters per day. It doesn't tell us what the starting point is, but an oil slick kind of makes it sound like this is like an oil spill. So I guess we could assume that at a point in time where 0 days have elapsed, how about that? That's the beginning. So I could say that the radius is 20 times d, the number of days. So in half a day, 10 meters, right? In 2 days, 40 meters. Express the area of the circle as a function of d. Okay, well, the area of the circle is pi r squared, right? So all I got to do is plug 20d into r to get the area as a function of the number of days. So pi times, in parentheses, this is important, in parentheses, the 20d is replacing r. And anything that happens to r afterward happens to 20d as a group. So that's then squared. So then I could say, okay, this is pi times 400 d squared, right? And if I want, as I typically would write this, 400 pi d squared. And basically that's it. And if you wanted to check your reasoning, you could say, okay, after 3 days, if the radius is increasing at a rate of 20 meters per day, that would be 60 meters, right? And so what would the area then be? Well, it'd be that squared times pi, right? And you can check that this formula gets the same result as this over here to see if that's right. So what would be 3,600 pi, right? So I wrote here as just a, but I could write this as a of, well, you know what? Let's not do it there, because I have r and d in the same line, two different input variables. But down here, I'll say, oh, this is a of d, right? As it's very clearly a function of d. So I can then say, okay, well, what's a of 3? A of 3 equals 400 pi times 3 squared, 9 times pi. Oh, that's right. So that's the same number as this one up here. So if I'm worried that I'm going to make an error in this, I can work out the formula and then separately just do it numerically with some, 3, 4, 5, pick some number, and see that my formula seems to get the right number when I do things numerically.